Okay, so last time on Thursday, we talked about boosting, AdaBoost algorithm, and provided this algorithm, which basically learned weak classifiers and added weak classifier to ensemble one by one. And this algorithm had several steps, like training a new weak classifier, computing its error, and then computing the coefficient. Okay, so it's difficult to see. Alpha t, which is the coefficient of the weak classifier in the ensemble, and then updating the weights in some certain way. So we discussed the intuition of what this is actually doing, but we didn't really derive why this is the right value for alpha or W. So they are intuitive, but they were not derived. So it took a while for people to understand why actually AdaBoost is working. So I think the early versions of it was more like a magic formula, that this is the formula of AdaBoost, and then this is working well. And then gradually there were some intuition of what it is doing. For example, there's an intuition of maximum margin maximization intuition, or things like that. What I'm going to do today is providing one derivations of AdaBoost, which seems to be quite clean, so you can follow it and see that we can derive all these kind of expressions. So we went through all these. So this brings us to this concept of additive models. In order to analyze AdaBoost, we introduced this additive model, which is a general way of thinking about models. Okay, so what is additive model? So consider some hypothesis class, H, with each hypothesis being a mapping from input to a binary output, -1 or +1. And each of these HIs belong to this class of hypothesis. So this is the space of your models. Think of it as, for example, a capital H is, or each H is a decision tree or decision stump, or linear classifier, or a support vector machine, any model that you have seen so far. So these are weak classifiers, and in this context, they're called bases. So these are each one basis in that space. So what is additive model? As the name suggests, it is just a combination of a linear combination, additive combination of m different terms for each of H being HIs belonging to that capital H. So we have HI, we have I1 to M of HIs, each of HIs belonging to calligraphic H. They're multiplied by some alpha I, which is a real valued number. And then the result of it would be H of M. So M indicates that we have M different additive models. And alpha I's is like we have 1 to M, so it's the whole thing is an M-dimensional vector belonging to Rm. And generally, we assume that they are non-negative. And sometimes we assume that they sum to 1. But it is not generally needed to be summed to 1. So that's what additive model. So what is important to observe here is that this is essentially the same form as the ensemble that we have in boosting. Boosting was combining an M different classifier, or capital T classifiers, or weak learners at the end of its procedure. And each of it, basically, the result would essentially look like this. So this is of the same form as the output of a boosting. Is this clear? Okay, perfect. So now the question is that we have this additive model, H of M, how we should learn it. So what does it mean by learning? By learning means that how to find each of HIs and how to find the corresponding alpha I's. One way to think about it is that we can learn all these M hypothesis HIs and all the coefficient alpha i's at the same time, which means that we have a loss function. So as usual, we have some loss function. We consider HM, take, for example, compute the output of them, compare with the true target TI. So at xn, compute it, and compare it with Tn for all n data points that we have, and then minimize over both all HIs and all alpha i's. So M hypothesis and M coefficient. So this is one way to learn it. But another way that we can actually do is that try to learn each of them one by one. So what we do is that we fix, for example, if you are at the nth stage of this training procedure, we consider H1 to HM to be fixed, but then learn HM plus 1. So in that case, the optimization, the corresponding optimization here only has H of M plus 1 and probably alpha of M plus 1, and not the previous hypothesis. So this is, do you see the similarity with AdaBoost? This second procedure?
Yeah, and the second one is what AdaBoost is doing.
It's exactly, yes, it is exactly like what AdaBoost is doing, that it fixes the previous weak classifiers and just add a new weak classifier at the iteration M, and then continue doing it. So the only difference here is that I use M, I think, index in the previous case. Here I'm using M. Okay, so the first approach, we actually will talk about it later, or something similar to it in the neural network lecture. But this approach is learning them one by one, is the approach that I'm going to talk about for the rest of this lecture. And it turns out that, well, we can see that this is very similar or exactly the same as what AdaBoost is doing, and with, of course, some details. And we can derive AdaBoost through this procedure. Okay, so how does this procedure look like? So this is a greedy procedure, because instead of learning all the hypotheses H1 to HM all together, we learn them one by one. So this is like grading computer science sense, that we add the, say, best classifier that locally improves the current classifier. You can think of it like this. So this greedy approach of fitting additive models is also sometimes known as stage-wise training. So training is done at stages. So how does it work? It starts from H0 being 0. We start from empty classifier, essentially. And for T iterations, for each of the iterations, we basically compute the M hypothesis as saying that HM is HM plus 1, previous hypothesis, or previous combination of hypotheses or basis, plus alpha M HM. So HM and alpha M is the thing that we want to find, but we assume that the HM minus 1 part is fixed. So what we do is that we want to find the minimizer of the loss function. So the loss function, where the model that we use has two parts: the part that is fixed, HM minus 1, and a part that is new. And this is, of course, the data, the target data, and XIs are the inputs. So we want to minimize the loss function over all data points n. And what is minimized here is the value of H belonging to a hypothesis class, and alpha, which is just a coefficient, real valued coefficient. So, and the result would be we get HM and alpha. And then we add it to the additive model to get a new HM by adding this new part to the previous part. So this is, again, this is very similar to boosting is doing, AdaBoost is doing. Okay, so so this is, I have defined like the stage-wise training additive models. I haven't talked about the choice of the loss function. We can choose any loss function, of course, in depending on what loss function would be most suitable. But I'm going to introduce first a new loss function, which is you haven't seen before, of course, and see that it has some nice properties. Okay, so the new loss function. So this is a classification problem. The new loss function is called exponential loss, and it is defined like this, that if basically your target, you compare your target with the output of your model, Z is the output of your model, and this Z here is not necessarily -1 or +1. This is essentially before computing the sign of that, your model. Very similar to what we had, for example, support vector machine or logistic regression. Logistic regression before having the output of linear model going through the logistic activation function. So that's the same Z. So this would be exponential of Z and T. And if we see how it looks like this orange curve. So just maybe take a look at this figure and see what components do we recognize. We had seen this before in the last lecture, or similar figure. There is one new addition. So we have the 0-1 loss, so the blue one that I'm showing there, which basically says that if the true, so this is assuming the true label is +1, so it's a positive label. If the prediction of model Z is positive, there is no loss. If it is negative, there would be some loss. And the loss would be exactly +1 for 0-1 loss. So what else do we have? We have the hinge loss. So hinge loss would be, it's kind of difficult to say. See, this is the hinge loss. So you see that it behaves linearly for values of Z smaller than +1 and 0 afterwards. And this is essentially, this region between 0 and 1 is the region that the label or the output is within the margin, essentially. So this is a margin enforcing loss. If we recall from the last session, that if the margin is large enough, then there would be no loss. But if we are kind of violating the margin, even not incorrectly, like maybe even the classifier is correct, but within the margin, there would be a linear cost for it. You also observe, I think, this logistic regression with cross entropy, logistic activation function and cross entropy loss, this one. So that's also another thing. The difference was that asymptotically, when the prediction is very bad, the loss function behaves like linear. But if the Z is positive, so it's a correct side of prediction, there would be some loss, but the loss function is kind of going to 0. And then we have this exponential loss, which is the new one. So this is the exponential loss, which you see that on the positive side, it behaves almost similar to logistic regression. But on the wrong side, it behaves exponentially. So if we are predicting incorrectly, the loss would increase exponentially depending on how large in absolute value the Z is. So this is another loss function for classification. And you see that it leads to interesting behavior. Any quick question? Okay. So now we consider the exponential loss function, and we consider this additive model and training of additive model through stage-wise training. So one component is additive model, the training is stage-wise, and then the loss that we use is exponential loss. And then the rest would be just some derivations to see what happens. So this is the loss function, stage-wise training, and additive model. So what we saw from previous slide, so this slide, so this is Stagewise training is doing. So we just find the H and alpha that affects only this time. And the H of m-1 was fixed. Okay, so what is happening? I'm just plugging it there. So we want to find at mth stage, hm and alpha m that minimizes the exponential loss of minus hm-1 of xi plus alpha h of xi. So alpha h is the part that is not fixed and is optimized. Hm part is fixed. So this is fixed. This is, we want to find it. And then we are multiplying by the target because of additive loss. So that's what we have. There was a question, yes.
So in the previous slide, when would you want to use the exponential loss? When would you prefer using it?
So that's a good question. So the question is that when do we prefer to use exponential loss? I don't have a very clear, well, so basically what we have in, say, classification or when we design a loss function, we first show that people probably come up with something that seems intuitive, that if you're on the correct side, we shouldn't penalize. If you're on the wrong side, we should penalize. And then depending on, and there are some different ways that we can penalize, like, for example, hinge loss, which has a geometric interpretation, or exponential, which says that we penalize a lot. But then afterwards, we have to show that doing this has some kind of nice properties. Like if we do this, does it lead to a classifier that has properties that we want? For example, has minimum or small, say, 0-1 loss, because that's what exactly eventually we want to do. If you recall, we started with 0-1 loss, but optimizing it was difficult. But say, for example, if we do exponential loss, is the optimization easy or not? And turns out, yes, for some cases it would be easy, and then it might have some nice properties. But in general, we can't say which one is better than the other one a priori. We have to compare them and see what the behavior would be. And each of these choices essentially leads to different algorithms. Like hinge loss would be SVM. If we choose cross-entropy and logistic activation, we get logistic regression. So your question would essentially become, which one is better, SVM or logistic regression? And both of them can be good. So there is a question as to why do we want to use exponential loss for additive models? So here, I'm just saying that let's choose the exponential loss. I'm introducing a new loss function and saying that let's see what happens with it. So later on, we see that why I did do some choice on this slide. I mean, of course, the connection is connection to AdaBoost. Okay, so through the training, so we want to find H and alpha. We added here, so the next line, I just divide the terms. So I have, I get exponential of minus hm-1 times t minus alpha h times t. So I just divided two terms. And then I'm using the property of exponential function to have exponential of addition of two things, that's the multiplication of each of them. So I have exponential of this term and then exponential of minus alpha h t. And I'm kind of ignoring the I part, but each of them has an index of I, which is the data point. So the important thing, and then I call this whole term as Wi of m. So this can be seen as a weight of on data point I using the model m-1 previous models. So the form that we get is interesting. So essentially we get a form of loss function, which is exponential of minus current hypothesis times t times some weight function, which basically says that how important is the weight of that training point. And the interpretation of that weight is essentially what is the loss of the previous models, combination of previous n-1 models on that training point I. So what we get here is that note that that W part does not depend on the H and alpha. So from the optimization perspective, we can just consider it as a constant. So what we want to now solve is that we want to solve WIM times this exponential loss that is applied to data point I using hypothesis H. Okay, so now what happens is that just consider two cases, like either H is predicting for some particular H, either prediction of H is correct or prediction is not correct. So either prediction is the same as the target. So if H of Xi is the same as Ti, what we get for that exponential term is exponential of minus alpha, for example, times +1 times +1 or times -1 times -1, which would be exponential of minus alpha. So that loss becomes, if the prediction is correct for some H, the loss would be exponential of minus alpha. And then if the prediction is incorrect, we get, say, +1, but the true label is -1. So we get exponential of plus alpha. So, and this is, of course, we are in the binary classification with minus and +1 outputs. If it was different, it would be very similar. If it was 0 and 1, it would be similar. So the result is that we can decompose the sum at the top of the page to two parts of data points that for that particular H we have misclassified and the data points that we have correctly classified. So how can be written this? This would be, if it's correct prediction, so H of Xi is equal to Ti. So this whole thing would be +1 times WIM. The whole summation is multiplied by e to the power of minus alpha. And then we have data points that are incorrectly classified, so which are identified by this HXI being different than TI, times again WI, but the whole thing is multiplied by e to the power of alpha. Okay. So there's a question here is that what set does H belong to? A small h? No, set is capital H, this one. So that's the hypothesis class, so the space of decision trees, for example. Okay, so this is, we divided the loss function to two parts, and then we see that this helps with the manipulation. So what we do is that we now add and subtract this term, which is e to the power of alpha minus alpha times summation over data points of WI of identity of H of Xi being different from Ti. So maybe I should give you a warning. I mean, this derivation seems a bit complicated, and they are a little bit complicated, so that's okay. It's okay if you don't follow each step. I mean, each step should be clear, but we are just doing some algebraic manipulation. So what happens is that, okay, so I'm adding and subtracting this term. So basically means that, okay, so this was from the previous page. So our loss function can be written to the correct prediction and incorrect prediction. And then I add these two terms, like +1 and -1. And then what we do is that you see that I kind of arranged e to the power of minus alphas on one side, and then we have e to the power of alpha minus e to the power of minus alpha the other side, but with the negative side. So what happens is that we get I from this part, I get this term. So e to the power of alpha minus e to the power of minus alpha times the summation over incorrect classification plus e to the power of minus alpha of wi's. Some of the terms are correctly classified and some of them are incorrectly classified. So what we have is that I to the indicator function of h being different from t plus indicator of h being equal to t. So why is that I've written that this whole thing is equal to 1? Why is that? Or is it clear why it's the case? Exactly. So it's either h is correct or h is incorrect. So one of them would be active at any time. So that's great because this makes the whole part here equal to 1. So what is left would be just weights, which are not a function of h, and alpha i's, which is again not function of h. And this first term, that is a function of h. Okay, so what we have now is that after all these simplifications, or after the last function that we started here, after these manipulations, we divided it to two parts. One part was e to the power of minus alpha, summation of the weights. And recall that the weights are fixed. It depends on the previous iteration. So the only thing that is learnable here essentially is alpha. And then the part that depends on h and alpha. So what is, I think, interesting to, so what we can do basically is that now if we want to optimize h, for example, we can focus on the terms that only depend on h. So what we have is that if we compute, I want to compute, say, arg mean of h and alpha, this would be equivalent of course, arg mean of the same things here. And then because the second term does not depend on alpha, on h, we can ignore it. We can just focus on the arg mean of this part for h. So let's first optimize h. What I'm doing here is that exactly that. The second term on the right-hand side does not depend on h. So we get that h of m would be arg mean of the first thing that we started, the loss, the exponential loss, which would be equivalent of arg mean of WIM times identity of with xi being different than ti. So you recognize that this term is the usual 0-1 loss. So this counts whether the classifier is correct or not. So this is the 0-1 loss. But what is the difference? The difference is that we have a weight W. So the difference is this part. So this would be, we have to minimize a weighted 0-1 loss function. So that's great. So for some some methods, we can actually solve this. For some methods, we cannot. For example, for decision trees, it is easy to minimize weighted 0-1 loss function. So let's get to. So suppose we can solve this. We solve this, we get this HM. Now we want to find alpha because that was the other thing that we wanted to compute. So suppose that we obtain HM, we want to find alpha. We find a weighted classification error, which would be exactly as the name suggests. So the cost of, so we have HM here, whether it's correct or not. So it's either 0 or 1, but is weighted by W, the weight. And then we define a normalizing factor. We divide it by a normalizing factor, which is the summation of all the weights. If the sum of the weights would be equal to 1, then the denominator would be 1. Otherwise, this is just normalizing. So with this definition and the fact that HM is argument of WIM exponential of minus alpha times t for each of the data points, we get that minimum of alpha of minimum over h of the loss would be, we plug in the result of h. So it would be minimum of alpha of e to the power of alpha minus e to the power of minus alpha times again both terms of that we had here. So we bring these two terms there. So it would be the summation, weighted summation of the misclassification loss plus e to the power of minus alpha times the weight. So what we want to optimize, of course, is the alphas. Other parts are just 0. So we do some manipulation and use the fact that definition of what the definition of error M is. So we use this to get that it would be minimum of all e to the power of alpha minus e to the power of minus alpha times error M times the summation of error weights plus e to the power of minus alpha, the summation of weights. So this is just algebraic manipulation. You can verify it later that this is indeed correct. We take derivative with respect to alpha and set it to 0 to find a minimizer of alpha. And if we do that, you get to this, that e to the power of 2 alpha should be 1 minus error M divided by error M. And if we solve for alpha, then you get that it would be half of log of 1 minus error M divided by error M. Okay, so now that we get those, how the weights are updated for the next iteration. So recall that we need to update so defined essentially weights like this. So weights at iteration M is like this. Now we added a new alpha and new M. So we got from h of M minus 1, we got to h of M. Now we just want to see what is Wi of M plus 1 essentially. Okay, so that's the weight. Wi of M plus 1 is exponential of minus HM. We divide it to two parts again. The previous part, h minus 1, and the new part, alpha M HM. Then use the property of exponential function to divide it to multiplicative form, or multiplicative form of exponential of minus HM minus 1 t times exponential of minus alpha M HM. This first part we already know it. We computed in the previous iteration. That was Wi of M. The second part is just the new part. So this is basically telling us what is the new weight would be after computing, adding the current hypothesis to our additive model. Okay. So let's just summarize. We started from additive model. We had a loss function. We said that let's choose loss function to be exponential loss, and then do the stage-wise training. So not training all of alphas and all h at the same time, but doing one by one. So we need to minimize h of M would be the minimizer of W weighted 0-1 loss. So if we know the weights, if we can solve this optimization problem, we get this new loss function. And this optimization problem may or may not be easy. So if we, for example, recall from a few lectures ago, where we argued that 0-1 loss is not easy to optimize, say if we have a linear model. But if we have, for example, decision tree, minimizing the 0-1 loss is actually is easy actually, because at each of the branches, at each of the nodes of the tree, if it is not weighted, the minimizer would be essentially the if it is not weighted, it would be the majority vote at that label. If it is weighted, then we need to consider the weight in computing the majority votes. But still, we can compute it easily. So that's why something like decision tree with this additive model is kind of compatible and kind of gets together very nicely. So that's HM. Computing alpha I is easy. We just need to know this weighted error, which we can compute easily. We know W's, we know HM, we compute alphas, and then the updating weights at the next iteration would also be easy because we take the previous weights and multiply by exponential of minus alpha m h of m times t. So if you go and compare it with several slides ago, this would be exactly the same update rules at AdaBoost. So what is happening is essentially, we showed that if we start with additive models, we do stage-wise training, and we choose a loss function that is exponential loss. What we get is AdaBoost algorithm. This insight wasn't how AdaBoost was derived. AdaBoost was derived more like, I think, similar to intuition I gave you, that we need to reweight the labels, the data points that are misclassified, and focus more on them. But we see that that is exactly, or can be interpreted as these additive models with exponential loss. And I think it took a few years before people could find this connection. So this is kind of, this was a kind of interesting development. Yes.
Sorry, can you clarify why using decision sponsor trees makes it easier to find the hypothesis with the 0, 1 loss?
Right. So so I can give you easily what is the okay. So no, actually, I guess in both cases, if it is not okay, so suppose first it's not weighted. Do you agree? Do you agree it is easy to find the right classifier or not?
You don't have, or I guess you're saying you don't have a, like the difficulty, we don't have a creation. So.
Right. Okay. So so I forgot to repeat the question. So the question is essentially why for decision trees finding this 0, 1 loss or weighted 0, 1 loss is easy, even though we don't have gradients. So that's right? That's kind of your question.
Sorry, okay, yeah.
Is it good? Okay, so maybe I just briefly say some of you have the question. So suppose we remember in decision trees, we had these different regions. Maybe one of the regions, we have classes or classes and circles. So essentially, if we have majority votes, if you have a 0, 1 loss, basically you need to find so you have these xi's. So you can focus on one of the regions and then try to minimize that region, each region separately, after we know this region. So basically, your hypothesis, you have many different hypotheses. Your hypothesis either provides outputs like cross or circle here. You can count the possibility of circle, or you can consider the case that it is outputting circle and see how many errors you make. And then you can consider another case that you always output crosses and compute the one that how many errors it is making. So for example, if the choice is say cross, the number of mistakes that we make in that region is 3. If we choose circle, So the best prediction there is just to choose cross. Now suppose this is the same, except that you have a weight. So you have a weight WI, it's some number. Again, you have two choices. Either you choose cross or you choose circle, but then this value would not be 3, but would be, you need to consider the misclassification times the weight of each of the classes, each of the data points. It would be a number. For example, it would be, I don't know, like 2.7. In another case, it might be 1.5. And in that case, you choose the label or the target or that region that has the minimum error.
Excuse me.
Okay.
I had one question too.
Okay, so there's a question, there's a comment that alpha, on this slide, alpha should be alpha M. That's right. So this would be the same alpha that goes here. So that will be the alpha. Okay, so that's a good.
Excuse me.
Okay.
I had a question too.
Ahmed, yes.
Yes. So you were talking about how it's easy to maximize or minimize the 0-1 loss for a decision stump, but just choosing which whether we output cross or circle for a given boundary is not the only decision we're making. We're also choosing the boundary, correct? But yes. I mean, I can see why it is still easy because you can just choose the boundary just a little bit before each data point and then see which one minimizes the error. But that's also a decision we're making, correct?
That's true. And you remember how we chose the boundaries in decision trees? Like we used some heuristics.
Yes.
Information gain, for example, it didn't have anything to do with even the loss function, the accuracy, but we chose something that was different.
Yeah, but in this case, we could just go straight for minimizing the loss function, and then we would have the optimal decision for that, correct?
I
think we're trying to just minimize loss.
You could, I mean, you could do that, but I mean, in the previous case, we were also minimizing the 0-1 loss. So that from that perspective, nothing changed. Whether for weighted classification, which the argument there was that there are cases that minimizing the 0-1 loss or the classification error is not a good idea because it doesn't essentially reduce uncertainty. And that was why we talked about information gain. It is not always the case that information gain is better, but in practice, it performs, I think, better for classification compared to the accuracy. If we make it to the case of weighted 0-1 loss, I'm not 100% sure whether this would be, whether information gain would be better or using the weighted accuracy would be better, but I don't see any reason that if previously we chose 0-1 information gain instead of unweighted accuracy, here we should change it to something else.
Yeah, yeah, that clarifies things. Thanks.
Okay, thanks. Okay, so this is okay, so that was AdaBoost. AdaBoost is minimizing exponential loss, or it was adaptive. So AdaBoost is interpreted as additive model with Stagewise training with exponential loss. This gives a suggestion. Actually, I think someone asked on chat before that why we choose exponential loss for additive models. We can do Stagewise training of additive models, but use other loss functions. So we can do other loss functions and try to go through this procedure. And we get a procedure, a boosting-like procedure, or it would be a boosting-like procedure, but it wouldn't be exactly AdaBoost. Whether the loss function The exponential loss had this nice structure that allowed us to do a lot of algebraic manipulation easily. Like exponential of two terms, the additive terms would divide basically, or they can be divided to, or rewritten as the multiplication of two exponential losses, and then one part was fixed, so that makes it much easier for manipulations. If we do other loss functions, it may not have the same property anymore. So it may make the optimization not as nice. But there has been a lot of work on trying other loss functions with this additive stage-wise training of additive models. Okay, so we have some, so this is just an application of AdaBoost. So this is a famous application, I think it's early 2000. So I guess 2001 probably, or 2002, which was a face detection algorithm. I'm not going through the detail much, but it was just saying that we could develop a very fast face detection algorithm or method system using AdaBoost. So I skipped the detail, and it could perform well for that time. Okay, so just summarize the boosting. Boosting reduces bias by generating an ensemble of big classifiers. Each classifier is trained to reduce the error of previous ensemble. And then it is in practice, it can't theoretically overfit, and it has been observed that it overfits, but is relatively resilient to overfitting. And then what we did is that going through this loss minimization viewpoint of AdaBoost. So originally, AdaBoost wasn't introduced as loss minimization. It was just like weighting of the data points. But we had this loss minimization, which just is covered. And it allows us to derive other boosting algorithms, for example, for regression, ranking, and things like that. So it was a big business at a few years ago, I think like 15 years ago, 20 years ago. Okay, then we have seen two ensemble methods. So this is a summary of ensemble methods. One was bagging, and the other was boosting. For bagging, the whole idea of ensemble is that we combine predictors, mostly classifiers or regressors, but we focus mostly on classifiers. We combine them to improve the performance. Boosting reduces bias, but increases variance. And technically, it can cause overfitting. It is sequential, so we add things, new classifiers, one by one. And then there would be high dependency between each of the elements of ensemble. We didn't really prove that or talk about that, but that's would be the case. We have the bagging, which the idea is that reduce the variance of the whole ensemble. Bias is not changed much because, I mean, it depends on how exactly we do it. For example, with random forest, because we are focusing on a randomly selected subset of attributes, we are adding some bias compared to the case that we consider all the attributes. But it's usually not changed much. It can be done in parallel. We just need to have samples from, we draw samples from our data set, and then we train each classifier. We classify separately, and then we combine them. And the goal is to kind of have a small correlation between ensemble of the elements of the ensemble. Okay, then summary of this whole this lecture on support vector machine, boosting, and kernel machine is that we saw support vector machine as a form of, we started from a geometric perspective to support vector machine, and then we derived a loss. We talked about margin maximization formulation, which is the geometric interpretation of it. From there, we derived the hinge loss, which was a new loss function in our kind of arsenal of loss functions of classification. And then we saw that if we go through the procedure, SVM or support vector classifiers can be seen as a minimizer of the hinge loss, and L2 regularizer. So then we had this issue of, okay, so this is a linear classifier. What should we do if we want to have more expressive classifiers? Then we talked about the concept of kernel-based methods, which was essentially we say that let's use a feature mapping, but then do, because of the properties of the SVM or linear model that SVM used, we saw that all the computation can be done by just computing the inner product of the feature mappings of each data point with others. So that allowed us to say that we have this concept of kernel function that computes this inner product in an implicit way without actually doing the feature mapping. So by introducing kernels, we can get the benefit of working with more expressive linear models in a more expressive space, like in expanded feature expanded space, without actually doing the expansion. And then I talked about this AdaBoost as another method for an ensemble method. And we saw that this is just solution of stage-wise training of additive model using exponential loss. Okay, so I think that's it. Is there any question?